Good morning. In this video, we are going to discuss about moment of inertia. Moment of inertia comes in dynamics part. In dynamics, the objects will be in motion. Okay. First, you see here it is represented by the letter I. Then here there are two parts. One is moment as well as inertia. Moment means it is a rotational agent. It gives rotational effect to the object. It rotates the object. Whereas inertia means it is the resistance offered by the object to the motion. Okay, so in simply, moment of inertia means it is the resistance to the motion or a resistance to the moment. Let us see the definition of moment of inertia. It is the property of an object that offers resistance to the moment. It comes in place whenever the moment tends to bend the body or the torque tries to rotate the body. Okay, normally any object, when you try to change the state of the object, it gives resistance. Okay, so this is what Newton's first law says. It says that every object continues in its state of rest or uniform motion unless it is acted upon by some external force. Okay, so this is what is known as inertia. Okay, it is a resistance offered by the body to change. Now let us take a translational motion. Translational motion which is created by a force. Okay, consider two objects m1 and m2. They are kept in a frictionless surface. Frictionless means this surface does not offer any resistance to the motion, where the friction force is 0. And here the mass is m1, here the mass is m2. m1 is less than m2. Now this is Newton's second law, a force equal to mass into acceleration. Now I am applying a same force, so of same magnitude. Now they will make a move in a linear way. That's what translational motion says. Translation means the object will be translated from this point to this point in a linear way. Okay, in a linear way, in a line. Okay, now these objects make a move and it has the acceleration of a1. Similarly, this object will also make a move, has the acceleration of a2. Here acceleration plays an important role. Acceleration means the rate of change of velocity with respect to time. Okay, it gives the measurement of how fast the speed changes in an object by the force. Okay, so here now from this equation f equal to ma, since force is same, the relationship will be something like a1 is greater than a2 because m1 is less than m2. Okay, so from this diagram or from this translational motion, it is evident that this mass offers resistance to the motion. Okay, mass offers resistance, so mass is a inertia. Now let us take another one example. It is a rotational motion. Rotational motion is created by a moment, and again I am going to consider the same masses m1 and m2, and I am going to fix this object. Okay, and applying a force at this point. Now distance between these two is r, so now this will create a moment, a rotational effect. Similarly, here the mass m2 is fixing at this point, force is applied at here. You see here also the distance is r, the same distance, so the moment is same in both the cases. Now this is alpha 1 and this is alpha 2, where alpha 1 alpha 2 represents the angular accelerations of the mass m1 and m2 respectively. Okay, angular acceleration, it plays the role of linear acceleration here. Now alpha 1 is greater than alpha 2. Okay, why? Because here the mass m1 is less than m2, hence the moment of inertia offered by this object is less when compared to this object. So alpha 1 is greater than alpha 2. Okay, here A1 is greater than A2 because of mass. Here alpha 1 is greater than alpha 2 because of moment of inertia. Now let us go to the next important thing. It is analog between mass and moment of inertia. Before going into that one, let us see the relationship between translational motion and rotational motion. Okay, and here is the diagram. Here is the moment point where this point is fixed and a force is applied at point A. Okay, so this is the initial position, and since the force is applied at here, force into distance creates a moment. So the moment tries to change this position from 0 1 to 0 1 dash. So this is the new position. Now if you take the point A, point A is shifted to A dash. Now this is the linear movement, translational motion. But this, if you look at here you have change in angle, so there is a rotational motion. So theta is angular displacement and S is the linear displacement of point A dash. Okay, now there is a relationship between these two, S and theta. S is a linear displacement and theta is the angular displacement. Let us see here now. This is linear displacement S, which is equal to R into theta. Theta is the angular displacement. R is nothing but this distance, the perpendicular distance. Similarly, V is the linear velocity, omega is the angular velocity. Now this is the relationship. And A is a linear acceleration and alpha is a angular acceleration. Now the relationship is A equal to R alpha. Okay, so this is the relationship between linear or translational motion to the rotational motion. Now let us go to the analog. Okay, consider the Newton's second law, F equal to mass into acceleration. Take this as the equation number 1. Now multiply the perpendicular distance on both sides. Here this is R and this is R. Now F into R, which is nothing but force into perpendicular distance, you know that it is a moment. Similarly, in the place of linear acceleration, substitute this value, A equal to R into alpha. So you will get the equation something like this. Now rearrange the equation in this form, like R into R square m R square alpha. Now this equation can also be written as m equal to I alpha, where I is nothing but moment of inertia. I equal to m R square. If you look at these two equations, 1 and 2, F, M are the inputs, A and alpha are the outputs, whereas M and I are the inertias. It is mass, here it is moment of inertia. Okay, clear? And moreover, this equation is not only mathematically derived, but it is verified through experiments. So it is accepted equation, where I equal to m R square, where m represents mass and R represents square of perpendicular distance. Next important thing is moment of inertia depends not only mass but also the distribution of mass. Second important information or knowledge is this one, distribution of mass. Now let us take a plate, and this is the plate. I am going to fix this end. Okay, and both ends I am applying a force. So this force now will create a moment. Okay, now you see here, this is the thickness. Now this plate gives you a moment of inertia. Okay, let me take that one as I1. Okay, now I am going to change the orientation, but the mass remains same mass. Here also m, here also m, but it is changed. Okay, like this. Now this end is fixed. I am applying a same force. Okay, but to your surprise, now the moment of inertia will be different, I2. I2. Okay, same mass but moment of inertia is different. Okay, moment of inertia is different. See here, moment of inertia depends upon mass into r square. Now these two terms are same in both the cases. Okay, let me take this one as r. Okay, r1, here also it is r1. Okay, now everything is same, you know that mass here also m, here also m, and r1 both are same, but the moment of inertia is different. Here it is I1, here it is I2. If you take the scale, you see here I am going to scale, but I am not sure how I can. Now I can bend the scale like this. If I apply a force at here, I can able to bend, but I cannot bend the scale when I apply a force at here. I cannot bend. Okay, because when you keep the scale like this, it gives, this is the material which gives me the resistance. But when I have the orientation of the scale like this entire mass or this entire thickness will give me the resistance. So one thing is sure here, the distribution of mass. Distribution of mass is very important in the case of moment of inertia. Though here mass and r is same, but both the orientation will give you the different moment of inertia. So this is also important thing to note. Okay, thank you. We will meet in the next video. Thank you.